thanks once again, Nathan, Airstreet, RAAIS, all my co-panelists and speakers today, as well as the audience for joining us. These are unusual times, and it's really great to have this opportunity to engage with everybody and tell you a little bit more about what we're doing at Cerebras to advance the frontiers of computing for AI. Cerebras Systems is a computer systems company. We are based in Silicon Valley, and we are out to build a new type of processor and a new class of computer system to fundamentally transform the compute landscape by accelerating compute for AI, not by a little bit, but by a lot. Multiple orders of magnitude beyond what's possible with traditional general purpose machines like GPUs. We were founded in 2016. We now have a world-class engineering team across hardware, software, machine learning research of more than 200 people. And we have offices now in San Diego and Toronto. I'd like to begin here, and I think this audience deeply appreciates this, that while we see across industries, whether they're health research applications, web scale data processing, fundamental science, AI has massive potential to transform the way that we live and work. But it is fundamentally limited by our computing technologies today. And we need a fundamentally new solution to unlock and accelerate deep learning. So let me break that down just a little bit. First of all, compute for deep learning is different, right? The neural network workload that is presented to a computer processor for deep learning is distinct from, say, graphics processing or database management. Massive computational requirements, right? Billions or trillions of operations, compute operations per sample introduced to a compute graph. Millions or billions of samples in training, which translates to peta or exascale compute. So you're starting at cluster or data center scale for many state-of-the-art models. Memory footprint is significant, gigabytes or more, weights, terabytes of data sets. And they also require high bandwidth communication. These are complex, often dynamic computational graphs with many neurons, many topologies of connections. At the end of the day, this often leads to days or weeks of compute time to train a state-of-the-art model on a large real-world data set. This is one of my favorite slides, one that was originally presented by Jeff Dean from Google back in 2017, but it illustrates the impact of long compute training times in research generally, but specifically deep learning. And what we see here is that, and we know this intimately as researchers, that long training times, if I have to wait days or weeks or months for my job to finish, at the extreme, I may not even try that experiment. In the interim, days to weeks, maybe I take some shortcuts, right? Maybe I use only a subset of the available training data. Or I train a smaller model as a proxy and then step forward. Or maybe take some of those lower value experiments off the table. All of those are compromises that are made in the face of a compute infrastructure that was fundamentally built for other work. The existing processors that we're using often have compute cores, that is silicon chips, that weren't optimized for deep learning. They have functional units for graphics processing or for very high precision physics-based mathematics for simulation. And they fundamentally weren't built for high bandwidth communication between processors. We see these iconic pictures of data centers with meters of cabling beautifully organized between machines to help them communicate at high bandwidth, but there's still significant overhead to clustering and scaling out. And moreover, as a software engineer or machine learning researcher, developing a distributed implementation of your model to run, say, data parallel in a scale out fashion over a large cluster of hundreds or even thousands of GPUs, we find, first of all, that the scaling is inefficient. We underutilize silicon often, and performance scaling is sublinear. Furthermore, those implementations of data parallel scale out models can be challenging to develop, and they are tied closely to the underlying infrastructure, so that if you change your neural network architecture or change or upgrade your cluster, you may need to reprogram the entire training job. So it's challenging, and it's not getting better in some sense. The challenge is growing. The chart on the right is work that was performed by some colleagues at OpenAI in 2018, and what they showed was that since 2012, the compute requirements for the largest AI training task have grown by 300,000x. There's an exponential rate of growth in compute requirements for deep learning. And the doubling time actually exceeds the doubling time of Moore's law. So in a sense, these results tell us that the requirements for deep learning compute are growing faster than traditional processor technologies can keep up. So if we acknowledge that the machines of today are suitable but not optimal, then what does the right solution for AI compute look like? First of all, we know that the right processor should have extraordinary compute capabilities. So many cores. And those cores should be flexible and programmable, but they should be optimized for the work that they're going to do. In the context of neural network compute, this is tensor-based sparse linear algebra operations. That processor should also have memory close to compute to be able to not only store the weights and activations of a model that's being executed, but be able to access those weights quickly and efficiently. And then high bandwidth communication to communicate the results of a given layer's operation, a given neuron's operation, downstream through the compute graph for training or inference at high efficiency and low latency. And last but not least, we know as hardware builders that if we're going to introduce a new processor architecture, a new platform, that it must be easy to use with the software that data scientists and ML researchers are using today. So with all of that in mind, we at Cerebras built the world's largest computer chip and the most powerful processor available today for deep learning. We call this the Cerebras Wafer Scale Engine. It's shown here on the left next to the largest chip built previously for scale on the right. So this is our Cerebras Wafer Scale Engine. This other chip is the NVIDIA Volta V100 GPU. So you can see this is not a small step forward in processor technology. This is a big step. It's designed from the ground up to deliver orders of magnitude performance gain for deep learning. This is an 8.5 inch by 8.5 inch unbroken piece of silicon. It's the largest square silicon chip you can cut out of the largest circular primary silicon wafer that's used for chip manufacturing. It's got 400,000 compute cores all on this chip, all designed to accelerate the tensor-based sparse linear algebra with deep learning. So you can think of these as all tensor cores. 18 gigabytes of on-chip memory. So the capacity to store even very large models weights all on chip at one time. And each core is directly connected to one another over a high bandwidth, low latency 2D interconnect mesh over silicon. This is orders of magnitude more interconnect communication bandwidth than is achievable with a cluster of traditional smaller form factor chips. So I'll break this down just a little bit from an architectural standpoint into compute and memory and communication and where we've made choices to optimize. At the core level, we show a schematic of our core on the right. This is a fully programmable core with a general set of instructions that are optimized for machine learning. And it is a data flow architecture that's optimized to handle sparse dynamic workloads. So work at the core level is triggered by the onset of data. And if that data is a sparse zero value, it has the ability to set that aside and only do useful work on non-zero values that drive your model towards convergence. From a memory architecture standpoint, a traditional memory architecture depicted here on the top at the right has a large shared memory bank over here that is separated from primary compute by a relatively narrow bandwidth link. This architecture is punishingly inefficient for frequent access of model weights and movement of data. The right answer, we think, for memory architecture for deep learning is what's shown down here on the bottom, which is a uniformly distributed memory architecture where all memory is accessible at high bandwidth directly from its associated compute core, and the data path can have full access and full performance from memory. From the communication standpoint, our chip of 400,000 cores has a 2D interconnect mesh on chip. So think of this as a cluster scale of compute that's directly networked on chip. So whereas a traditional cluster, in order to communicate between processors, you have to write out to memory, out over a PCIe bus, out through a network card, over copper or fiber, across racks or rows of racks in a data center. Our chip, by comparison, can communicate hop to hop, core to core in a single clock cycle, with tremendous power efficiency gains over a cluster of traditional machines. And that on-chip network is fully configurable to the communication pattern expressed by the users when they program the device. So this is a unique high-performance, large-scale processor for deep learning. But it naturally raises the question, how do we program this device? For that, we built a software platform, and our software stack has a primary task, which is to automatically compile a user's training or inference program to an executable that can run on a device. That stack is illustrated here. So we start today in TensorFlow. Our software extracts a representation of the user's training or inference compute graph and translates it into an intermediate representation, which is effectively the top of our software stack. This intermediate representation describes the compute requirements at every layer of the network and the communication pattern between them. And our software then automatically matches a high-performance kernel from our software library to each and every layer of the compute graph. That kernel representation of the compute graph expresses compute requirements, memory requirements, and communication requirements to our compiler, which then allocates compute and memory on our massive array to each and every layer. We can thereby execute your n-layer neural network as an n-stage data flow pipeline all on chip. So we compile and natively execute all layers of your network at one time in a layer parallel pipelined fashion on chip. We wrap up that execution plan and link it down to our device. So this is programmable with today's ML frameworks from the top with a library of high performance deep learning ops. We also have a set of lower level APIs into each one of these layers and are building a software development kit so that you as a user can extend or customize our kernel library to support your deep learning application or even applications beyond deep learning, such as high performance computing, physics-based simulation, or signal processing. And the goal overall then is to make this unique high performance computing resource programmable as a single node. We've covered the chip and the software, and the last step for us to take was to think about this from a whole system standpoint. This massive processing engine wasn't going to fit easily into a desktop machine or a 1U standard data center server. And so at Cerebras, we had to take a full systems perspective on how to deliver this solution and make it easy to install and deploy, operate, and manage in a data center. For that, we built the Cerebras CS1. This is powered by a single Wafer Scale Engine. The machine itself is about 26 inches tall, or if you're familiar with data center terms, it's a 15 RU standard rack compliant server. So it takes up about 1/3 of a standard rack. This server delivers the deep learning compute performance of many racks of traditional general purpose compute servers in a single unit, less than a single rack. We take 20 kilowatts of power into the device and have 1.2 terabits per second IO over 12 standard 100 gigabit Ethernet lanes. So the server has been built to be easily deployed into a data center rack and deliver the performance of a cluster in a single node. From a user standpoint, though, what does this really deliver? We're already seeing multiple orders of magnitude performance gain and reduction in wall clock training time across multiple neural network architectures from multiple industry segments. But at a practical level, what that reduction in wall clock training time equates to is, from a researcher's standpoint, the ability to test hundreds or even thousands of hypotheses in the time that it normally takes them to train one model. With the ability to increase my experimental throughput, or for a model that's in production, increase the cadence that I can retrain my model so that it best represents the real world phenomena that I'm trying to represent. Or allow me to bring maybe hundreds or thousands of X larger data sets to my model to build a more accurate representation. From an inference time, you can think about inference on this device as being in milliseconds to microseconds. Even for extraordinarily high throughput at very low batch sizes, we can operate this device for training or for inference at full utilization down to batch size 1. Which leads me to, I think, what is perhaps the greatest benefit of this device, which is that we didn't build this just to accelerate the neural network architectures of today, but rather as a platform for researchers to explore new types of neural network architectures, new ML methods or algorithms such as small batch training or extraordinarily sparse representations, sparse models that may not be practical or efficient or even possible on today's infrastructure. So with that, I'll say thank you. I think we should have some time for questions, at least a few, but I'm very pleased to have the opportunity to introduce the CS1 to you today. This system was designed and built to accelerate research and applied AI for the kind of work that I'm sure you and your teams are doing by orders of magnitude beyond legacy solutions. From a business standpoint, we're seeing massive and growing demand already, and acceleration for many of our early users' applications. By way of example, the system on the right is installed at one of our first publicly acknowledged customer sites. This system is at Argonne National Laboratories. It's a US Department of Energy scientific supercomputing facility. They're using the system to accelerate research on models ranging from cancer drug discovery to processing data for fundamental astrophysics, and most recently built and are running models on this device to accelerate research into potential therapies and cures for COVID-19. So while it's true that we're seeing extraordinary demand in industry, and I think it's very likely where we will scale, particularly for me as someone with a scientific and research background, it's extraordinarily exciting to see some of our first users using our system to power research into energy, environment, and human health. And I can't wait to see what comes next. So thank you, and I'm happy to answer any questions.